Hello again. I hope you enjoyed Molly's animation on resting membrane potential. We may hear from her again. Our next topic in neurophysiology is the action potential. Now that you know how the membrane establishes and maintains the resting potential, we can move on to learning about how an action potential is propagated along an axon. Molly explained how the resting membrane potential can be measured using a voltmeter, and that in a neuron the resting membrane potential is approximately negative 70 millivolts. Now, this voltage can and will shift depending on what is going on in the environment and what's happening with the neuron at its dendrites and soma. In the previous video we looked at special membrane proteins that establish and maintain the resting membrane potential. The sodium and potassium channels are considered leaky channels and are always open, allowing sodium and potassium to move down their concentration gradients. Whereas the sodium-potassium pump is considered a carrier protein that pumps sodium and potassium against their concentration gradients. When discussing the action potential, there are a couple more channel proteins that we need to describe. These are the gated channel proteins. Gated channels are not always open, but respond to some sort of stimulus. There are three types of gated channels, but we will concentrate on two. And these are the chemically and voltage-gated channels. Let's take a look at these two channels more closely. A chemically gated channel is also known as a receptor, and it contains a binding site for a chemical or ligand, such as a neurotransmitter. Whereas voltage-gated channels will open and close in response to changes in membrane potential. When these gated channels open, ions will diffuse quickly across the membrane, causing temporary electrical changes in the area of the membrane. These ions will be moving along electrochemical gradients and are the basis for all electrical events in a neuron. Take some time to familiarize yourself with these following terms. You can find definitions of these on pages 359 to 363. We will be looking at the events of the action potential. Before we do, please be aware that the events that will follow do not describe the initial changes that take place in a neuron that lead up to the action potential. We begin our study with the opening of the voltage-gated sodium channels. These channels open when there is a change in membrane potential, and we're not going to describe how that change has come about just yet. So get ready for another animation with Molly.
Neurons send signals over long distances by generating and propagating action potentials. Most action potentials originate near the axon hillock of the cell body, in the initial segment of the axon. It then travels the entire length of the axon. A closer look reveals that during an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts. At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through leak channels only and the membrane potential returns to the resting state of minus 70 millivolts. The neuron is now ready to fire another action potential. Summary: generation of an action potential. A threshold stimulus opens voltage-gated sodium channels. Sodium ions diffuse into the axon, depolarizing it to plus 30 millivolts. Voltage-gated sodium channels close, and voltage-gated potassium channels open. Potassium ions diffuse out of the axon, repolarizing it to a negative value. The membrane potential briefly hyperpolarizes. Voltage-gated potassium channels close, and the membrane returns to the resting state of minus 70 millivolts.
Thanks again, Molly. As always, you've done a great job. So let's recap the events of the action potential. During the resting state, the sodium and potassium voltage-gated channels are closed and inactivated, and the membrane potential is around negative 70 millivolts. A local change in the charge of the membrane causes the interior of the membrane to get less negative. This is known as a depolarization. If that change is strong enough and threshold is reached, which is around negative 55 millivolts, then the action potential will happen. Once threshold is reached, the voltage-gated sodium channels will open, changing the interior of the cell from negative to positive, continuing the depolarization to approximately positive 30 millivolts. This shift in voltage from negative to positive activates potassium channels to open and inactivates sodium channels. As potassium rushes out of the cell, the interior of the cell becomes less positive, and this is known as repolarization. There is a slight overshoot of repolarization such that the interior of the membrane becomes slightly more negative than resting state, and this is known as hyperpolarization. During hyperpolarization, that segment of the membrane is more difficult to depolarize again, and this is known as the refractory period. So there you have the events of the action potential. In our next video, we will look at the action potential in a myelinated versus an unmyelinated axon. And we will also be looking at the events that occur at the synapse that lead up to the action potential. Until then, be well.